So, here we go with this target. I can use Avogadro's number to express the number of atoms in terms of moles. So, let's look at this balanced equation. Cu2s plus 2O2 yields 2CuO plus SO2. Okay? What does it mean? How can we interpret this information? Well, this is how. We can say that we have one Fu of Cu2s plus 2 molecules of O2 to form 2 Fu of CuO plus 1 molecule of SO2. Some of you are snickering, probably because you think it's funny that I'm using the abbreviation FU. Well, you know what FU stands for? Yes. Stands for formula unit. And what is the difference between formula units and molecules? You see, ionic compounds are made up of metal nonmetals. They are not molecules. Those are molecular compounds. So what do we call the smallest subunit of an ionic compound? We have decided to call it formula unit and abbreviate it as FU. Bailey, it's FU. Okay? And that stands for the smallest particle of an ionic compound. You need to be familiar with that. Okay? And you don't need to think of any other abbreviation of what it could possibly stand for other than formula unit. So the next time somebody says FU to you, say, no, I'm actually made up of mostly molecules. You should call me molecule, not an FU. Okay? And they'll realize at that point that you really do know what you're talking about, and they will have newfound respect for you.
You sure?
Yes, I've tried it out.
Making sure.
Or are they just confused and they just kind of walk away from it?
Well, if they're confused, it's probably because they're not intelligent enough to understand the concept, and they should walk away. They should. Because to be in your presence is not worthy.
What if they don't? Beat them up.
Right?
Then you'll have to explain it to them in smaller words that they might understand.
What if they beat you up?
Then they did not deserve to be around you, so maybe you should just deal with it. Molecule is the smallest subunit of a molecule, a non-metal non-metal. Is this equation very practical? If you're a copper refinery owner who wants to know how much sulfur dioxide, air pollutant, will be released by the roasting of copper 1 sulfide. If the EPA wants you to determine how much sulfur dioxide you're putting out into the atmosphere, is it going to be very practical to talk about the bazillion of molecules that you're No, they're going to want to know things in terms of liters or grams of sulfur dioxide that are being emitted. So that balanced equation is wondrous and beautiful, but it's not very practical. There has to be a way of converting those numbers into numbers that are, well, numbers that can be measured, like liters and grams. So, let's begin by explaining to you a little bit about how this all works.
None of this solves my tea sweetening problem. Like, I don't know how many AMUs of these molecules together are going to make this taste good. But none of this solves my tea sweetening problem.
We're still having technical difficulties.
Is your volume turned down?
My volume's turned down. Why is my volume turned down?
But none of this solves my tea sweetening problem. Like, I don't know how many AMUs of these molecules together are gonna make this taste good to me, or how many molecules of sugar I can consume while maintaining my slim yet robust physique. This doesn't happen by itself, you know. In order to make these calculations and predict reactions, I first need to be able to convert the atomic mass of this sugar into a standard amount of substance. Not weight, not volume, just purely objective amount of stuff. You heard me. Stuff. That, my friends, is what moles are for. Not those moles. Those are nice-looking moles. A mole is arguably the most important unit in all of chemistry because it allows us to express a chemical's atomic mass in terms of grams. And to define what a mole is, no matter what it's a mole of, we use our old standby carbon-12. There are 6.022 times 10 to the 23rd atoms in 12 grams of carbon-12, and by definition, that number of anything is a mole of that thing. That's a lot, and it is known as Avogadro's number, one of the most important constants in chemistry, and although Avogadro isn't the one who arrived at this number, it's named in his honor because he used this basic principle of comparing amounts of substances to first weigh atoms and molecules. So there are this many carbon atoms in a mole of carbon-12, and there are the same number of anything in a mole of anything else. Like a dozen roses is 12 roses, but a mole of roses is 6.022 times 10 to the 23rd roses, which would be enough roses to cover the surface of the earth quite deep. A mole of sand would be 6.022 times 10 to the 23rd grains of sand, and if they were each 1 millimeter long, a mole of them would stretch 100 quadrillion kilometers. So you get the picture? It's a big number. But in chemistry, the thing to remember is this. A mole of any element contains 6.022 times 10 to the 23rd atoms of that element, no matter what. This is what lets us translate numbers of atoms into grams. It lets us weigh the element.
All right. So what is the secret of converting things that can be found in a balanced equation to units that we can use to measure stuff? It's the mole. The mole. Okay, so one little FU of NaCl is insignificant. We can't see it, we can't measure it, we're not even sure it exists. But if you have enough of those FUs, then maybe, just maybe, we have enough to be able to see, and therefore enough to be able to measure. And that's where a mole comes in. What is a mole? A mole is small and furry. Okay, no, it is not. It stands for a particular number of things. Eggs are so small that we don't sell them in ones. We sell them by the dozen. Okay? A gross is a dozen dozens. So if you have a gross, you buy pencils by the gross, which is 144. Paper is so thin and hard to transport, it would be a whole lot better if we could measure paper not by the sheet but by the package. So we package them in groups of 500. We call that a ream. So we are already used to terms that we use to describe packages of things that it's just a whole lot more practical for us to deal with. Well, the mole is going to be the same thing. Unfortunately for us, where an egg is big enough for us to count, atoms are so small that we can't see. So where an egg, 12 eggs, is enough for us to handle in our hands, 12 atoms, if we were to place it in the palm of our hands, we would not see. Not even 12,000. Not even 12 million, not even 12 billion, or trillion, or quadrillion, or quintillion. Folks, it's only until we get to have this many carbon atoms that we have enough to be able to hold in the palm of our hands. 6.02 times 10 to the 23rd. This number is called Avogadro's number, and it was named after an Italian chemist who got us started, who basically, what he came up with led to us coming up with this number. He did not invent the number, but he got us started.
It took an Italian house elf, genius, Lorenzo Romano Amadeo Carlo Avogadro di Guardia di Ceretto. Did the first time. We'll just call him Amadeo Avogadro, but he was a count, so he had to have a super fancy name, and I'm me, so I had to try to say it. Much like Lavoisier, Avogadro's political alliances would get him into trouble. After Napoleon's downfall in 1815, Avogadro was active in the Italian anti-monarchy revolution, possibly even sponsoring some revolutionaries with his personal fortune. For this, he lost his chair at the University of Turin, but thankfully he did not lose his head. Avogadro proposed, correctly, that any gas in a container of the same size with the same temperature and pressure would have roughly the same number of molecules in it no matter what the gas was. So any difference in mass between two flasks of the same size full of two different gases would be because of a difference in the actual physical mass of the molecules. And thus, Avogadro basically figured out how to weigh atoms and molecules, as long as they were gaseous. To support his hypothesis, which was certainly good enough to support, he suggested that in forming water, oxygen gas would actually split into two oxygen atoms, what he called elementary molecules that could not be broken down any further. For some 50 years, Avogadro's idea of fundamental molecules were ignored, maybe because of incorrect ideas about how atoms stuck together, maybe because Italy was a bit of a backwater of science and Avogadro wasn't considered an important thinker at the time. But the scientific community, as it usually does, came back around to Avogadro's ideas eventually, not only naming his proposal that equal volumes at the same temperature and pressure contain the same number of molecules of Avogadro's law, but also giving him his own number, maybe the most important number in chemistry, certainly one of my very favorite numbers, but we'll get to that later.
So how big is this number? If you were to string a mole of paperclips around the Earth, it would circle the Earth 50 trillion times. Nevertheless, how big is a mole of water molecules? Big enough to hold in your mouth. A gulp of water is about a mole of water. A mole of water is about a gulp of water.
Been with me for a couple of weeks, and I do hope you have. You're probably thinking to yourself, wait, no, don't we already have a way of measuring elements? And you're right, we do. The real coin of the realm when it comes to measuring stuff in chemistry is relative atomic mass, the average atomic mass of all of the naturally occurring isotopes of a given element. So, for example, all of the natural carbon on Earth occurs as one of three and only three isotopes, C12, C13, and C14. They all have 6 protons, but the number of neutrons vary. And these isotopes show up on our planet in totally different proportions. So the relative atomic mass of carbon is a weighted average of these 3 masses, which comes out to 12.01. But 12.01 what? Well, remember when we were talking about units of measurement, we were talking about arbitrary talk. Most units, except for the ones that we use to measure time, aren't based on any real objective value. We just pick a unit, like the kilogram, and we agree for a standard on what a kilogram is, and then we run with it. The same goes for atomic mass. We measure atomic mass in atomic mass units. We make them up, and the value for a single AMU is, bear with me now, 1/12 of the mass of an atom of carbon-12. Why? Funny story. Until the mid-1800s, chemists in different parts of the world used different yardsticks for measuring elements. One of the most intuitive, and therefore most common, was to use the smallest, simplest element, hydrogen, as a baseline. But in the 1850s, some chemists, led by German Wilhelm Ostwald, proposed using oxygen instead. They preferred oxygen mainly because it combined readily with so many other elements, so they figured it would be easier to determine the weights of lots of compounds. So a bunch of guys stroked their beards, agonized over this for years, until in 1903 they decided that atomic weight, as it was called, should be measured in 1/16 of an oxygen atom. Until in 1912, isotopes were discovered and chemists realized that you can't talk about an element like it's all the same thing. It turned out there was an oxygen 16, and an oxygen 17, and an oxygen 18, and suddenly everyone was walking around like, I don't know how much this stuff weighs anymore. This was so crazily disruptive that it took another 50 years of strokey beard meetings for everyone to decide to use another standard, carbon-12. Like oxygen, carbon is common and kind of promiscuous when it comes to what it bonds with, and since it has 12 protons and neutrons, the mass of other similar elements could easily be expressed as some fraction of it. So, since 1961, science has pegged 1 AMU as 1/12 of an atom of carbon-12, which means that carbon has a relative atomic mass of 12.01 AMU, oxygen 16 AMU, and hydrogen 1.008 AMU. So that's how we weigh atoms.
So how does this help us? Well, here we go. Why is the mole so useful in chemistry? Because atoms, FUs, and molecules are so small that only when you're dealing with 1 mole amount can you be dealing with handy amounts. What is the relationship between what he just told us and the mole? And this is what we're going to learn next. 1 mole of any atom is equal to its atomic mass in grams. So those 12 AMUs, if you're dealing, that is the mass of 1 atom of carbon, not practical. But if you're dealing with mole of carbon, that 12 becomes 12 grams.